Section 7.4, Similarity in right triangles. Theorem 7.3, the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Here I have a triangle, A, B, C. It's a right triangle. The right angle is at vertice C. I also have a segment CD that is an altitude from the right angle to the hypotenuse. When this occurs, I generate three triangles that are similar to each other. The two smaller ones, which are going to be triangle ACD and triangle CBD, are similar to each other and to the original triangle ABC. Knowing the similarity statements, I can determine the congruent angles in each of the similar triangles and also the ratios of the segments of each set of similar triangles. The altitude to the hypotenuse in a right triangle generates an interesting proportion, a proportion known as a geometric mean. A geometric mean is a proportion in which the means are equal. Here, I have a ratio A is to B equals C is to D. In other words, here B and C are my means, A and D are my extremes. Also, recall that we can set this up as A over B equals C over D. In the geometric mean, it's telling us that the means are equal. In other words, it would look more like this. A over X equals X over D. Similar proportions as before, except in this case, my means are equal. The geometric mean of A and B is the positive number X such that, here again I have A over X, X over B equals, and when I do the cross product, I'm going to get X squared is equal to A times B. To solve for X, I just take the square root of both sides, and I achieve at the answer, X equals the square root AB. And since I'm talking about a length of a triangle, or segments in a triangle, that's why I have a situation where I have a positive number for my value for X. We're going to use a proportion with the geometric mean when we deal with a altitude drawn to the hypotenuse of a right triangle. Therefore, we have to learn how to set up a proportion with a geometric mean. Here, I need to find the mean of each pair of numbers. I'm given two numbers in each of these examples, and I'm going to use that as a geometric mean. To do that, I set up a proportion in such a way that my means are equal. Since they are unknown, I'm going to set them equal to X and X. Now I have means that are equal, and my ratios are 2 to X equals X is to 9. Then I solve using a cross product. X times X is X squared. 2 times 9 is 18. Take the square root of both sides. X equals, and here I simplify. Remember from the previous video, we know how to simplify the square root of 18. I break this up into two numbers. One is a perfect square. Therefore, 9 times 2. Here are my two factors. One's a perfect square, and that's going to give me the square root of 9, which is 3 square roots of 2. Again, they want us to find the geometric mean between 27 and 3. I set up a proportion. The means are equal, and it's going to be 27 to X equals X is to 3. I use a cross product. X squared is equal to 3 times 27 is going to give me 81. The square root of both sides, and I get a value of X equal to 9. The next example, I'm going to have a proportion. My means are going to be equal. They want to find the geometric mean between 7 and 14. Cross product, and I get X squared is equal to 98. Take the square root of both sides. Simplifying 98. gives me the square root of the factors of 49 and 2, one of which is a perfect square. Therefore, x is equal to the square root of 49 and 7 square roots of 2. Prior to looking at theorems based on an altitude drawn to the hypotenuse of a right triangle, we need to make sure we know the parts of a right triangle when that relationship occurs. Notice we have 3 right triangles drawn inside of this figure. The large one, and set on the inside of the figure is a right triangle to the left and to the right of my altitude. When I identify parts of my right triangle when I have an altitude drawn to the hypotenuse, I must identify the parts based on the large triangle. Therefore, the segments that form the main right angle are the legs. I know I have legs in the interior of my triangle based on the 2 small right triangles, but recall, everything is based on the large right triangle. Also, from the right angle, the opposite segment we know is the hypotenuse. I also know the entire segment is that hypotenuse. And I say that because we're going to break that hypotenuse into 2 segments. Those segments are broken up by the altitude. Therefore, these are the segments of the hypotenuse. And this is a segment of the hypotenuse. And I can go further by identifying this segment is adjacent to that leg. And this segment is adjacent to that leg. And that becomes very, very important when I'm going to deal with the theorems related to the altitude drawn to the hypotenuse of a right triangle. Here we have corollary 1 to theorem 7.3. If an altitude is drawn to the hypotenuse of a right triangle, then the altitude is the geometric mean of the segments of the hypotenuse. Recall, we already defined the segments of the hypotenuse in this figure. We know that we have the left of the altitude is the segments of the hypotenuse, and also to the right of the altitude is another segment of the hypotenuse. We already know that the altitude is a segment from a vertex that is perpendicular to the opposite side. In this case, it's to the hypotenuse. And we know when I'm given a geometric mean, as stated in our corollary, that the altitude is the geometric mean. Therefore, if I have a figure similar to this, I know my altitude is the geometric mean. And the segments of the hypotenuse are what the altitude fall between. Therefore, this is a segment of the hypotenuse and segment of the hypotenuse. It doesn't matter in which order these 2 fall. It just matters that my altitude is the geometric mean. A quick example could be x, and my segments equal 3 and 8. Therefore, if this occurred, I know I have an altitude that's a geometric mean. A geometric mean is a proportion in such a way that my means are equal. Here, my altitude is unknown, therefore x and x. And it's the geometric mean between the segments of the hypotenuse, which are 8 and 3. Therefore, x squared is equal to 24. Take the square root of both sides, and I have x equal to, I simplify the square root of 24, 2 factors being 4 times 6, and that gives me x equal to 2 square roots of 6. Corollary 2 to theorem 7.3. If an altitude is drawn to the hypotenuse of a right triangle, which we have here, then each leg is the geometric mean to the hypotenuse and the segment of the hypotenuse adjacent to that leg. On the previous slides, we defined the legs and the segments of the hypotenuse. So here, if I take a look at this leg, and with that leg, this is the segment of the hypotenuse adjacent to that leg. And of course, we know the entire segment is the hypotenuse. Therefore, I can set up a geometric mean with this leg. And we know a geometric mean is a proportion where the means are equal. In this case, the legs are the means. So here, this leg is the geometric mean. And it's the geometric mean between this segment of the hypotenuse and the entire hypotenuse. As previously defined, I know that I have two legs. Therefore, this leg is a geometric mean between the hypotenuse, which I already have, but it's also between the segment of the hypotenuse adjacent to this leg, which is this little segment. Therefore, again, I can set up another proportion in such a way that that leg is the geometric mean, and my means are now equal, but this leg is the geometric mean between the entire hypotenuse, which is in both of these proportions, but the difference is this is between this segment of the hypotenuse adjacent to that leg. Let's look at an example related to our previous two corollaries. Here they want us to find the value of the variables. I'm given a right triangle and an altitude drawn to the hypotenuse. I'm given leg A, leg B, and altitude H. I'm given a segment of the hypotenuse, measuring here 7, that is adjacent to leg A, and a segment of the hypotenuse 3, adjacent to leg B. Therefore, I do know the entire hypotenuse is 10, just adding those two segments together. Now, I can just start with one of the corollaries. In this situation, given the measure of the hypotenuse and each segment, I can start with either of my two legs or the altitude. I'm going to start with A, but this could be your choice. And I use the corollary related to that segment. Here it is a leg. Therefore, that would be corollary 2. I call it the leg theorem. When an altitude is drawn to the hypotenuse of a right triangle, then that leg is the geometric mean between the hypotenuse, 10, and the segment of the hypotenuse adjacent to that leg, 7. Then I just solve by cross product. A squared equals 70. I take the square root of both sides, and A equals the square root of 70. That's already simplified. I'm going to choose now to do the other leg. That's B. And again, my leg corollary, which was corollary 2. When an altitude is drawn to the hypotenuse of a right triangle, that leg is the geometric mean between the hypotenuse, which is 10, and the segment of the hypotenuse adjacent to that leg, which is 3. So you can see that these two proportions are very similar. It just depends on the segment adjacent to which leg we're dealing with. Then I cross product. B squared is equal to 30. Take the square root of both sides, and I get B equal to the square root of 30, and that is simplified. And my last segment I need to solve for is my altitude, corollary 1. If an altitude is drawn to the hypotenuse of a right triangle, then that altitude is the geometric mean between the segments of the hypotenuse, here 7 and 3. Cross product, h squared is equal to 21. Take the square root of both sides, and h is equal to the square root of 21. Again, that is simplified. On my next diagram, I have a right triangle. I have an altitude drawn to the hypotenuse of that right triangle. Again, we want to find the values of our variables, x, z, y, and here k. Let's start out by choosing a segment to solve for. if I start with one of the legs, I will set up a proportion and use corollary 2, which means the leg is the geometric mean between the hypotenuse, k, and the segment of the hypotenuse adjacent to the leg, which is 4. In this proportion, I have two unknowns, and therefore I cannot solve for those unknowns. So this proportion doesn't get us anywhere. Therefore, your next instinctive move would be to solve for z. And in this case, again, I would use corollary 2, which is the leg corollary. And if that leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg, which is y. And this proportion doesn't get us any closer because now I have 3 unknowns and can't solve for any of these. Therefore, this procedure must not be the way to go. Therefore, when doing problems like this, I need to move rapidly and also instinctively to see what direction to go to solve for different variables inside my problem. The only other corollary I could use is the one on the altitude, but I already know the altitude. But let's see where this gets us. Corollary 1 says if an altitude is drawn to the hypotenuse of a right triangle, which we have, then that altitude is the geometric mean. And it's the geometric mean between the two segments of the hypotenuse, which are 4 and y. Now I can use the cross product rule and get 4y equal to 4, and y is equal to 1. Now that gives me the length of that segment, and also when I add them together, I get the length of the entire hypotenuse. Now with that information using corollary 1, I can then go back and solve for x and y using corollary 2. Let's just erase these two proportions and do that. I'm going to start out by solving for y. Again, that's corollary 2. That is the geometric mean between the hypotenuse, which I know now is 5, and the segment of the hypotenuse adjacent to that leg, which is 4. That gives me x squared is equal to 20. And the square root of both sides, then I separate that into two factors. One's a perfect square, 4 and 5. And I get x equal to, the square root of 4 is 2, square roots of 5. Now I go back and finish the other leg, which is z, using, again, corollary 2. That leg is the geometric mean between the hypotenuse, which is 5, and the segment of the hypotenuse adjacent to that leg, which is 1. Cross product, z squared equals 5, square root of both sides, z equals the square root of 5. Therefore, when doing problems, I just don't look for the variable to solve for. I look for a proportion to set up that has one unknown variable. Then I can use that information in the diagram to get more information for my other unknown legs or segments. Again, I have a diagram that's a right triangle, and I have an altitude drawn to the hypotenuse, and I want to determine the value of these variables. First instinct is to start with the variable z or y. But in both cases, if I choose z, I have a leg, therefore it's the geometric mean to the hypotenuse, which is known, but I don't know the segment of the hypotenuse, so I'll have two unknowns. The altitude is the geometric mean between the segments of the hypotenuse, and I don't know either of them. Therefore, that would still give me two unknowns within one proportion. So these two, z and y, are not the variables I want to start with. Therefore, I want to start with 18. 18 is a geometric mean because it is a leg of the right triangle. And that leg is the geometric mean between the hypotenuse, which is 36, and the segment of the hypotenuse adjacent to that leg, which I'm going to let be x. Then I can just solve for x by the cross product rule, and that gives me 36x is equal to 324. Then I just divide by 36 on both sides. I get x equal to 9. So the length of this segment is 9. 9 from 36 gives me the length of the other segment of the hypotenuse, which must be 27. Now I can find the value of z. So again, z is a leg, and by corollary 2, that leg is the geometric mean between the hypotenuse, which is 36, and the segment of the hypotenuse adjacent to the leg, which is 27. Cross product, I get z squared equal to, and I'm going to leave these factors as they are instead of multiply them, 36 times 27. If I multiply them, I'm going to get a very large number and find a difficult time of finding a perfect square. But here, I can work with the two smaller ones and use the rules of square roots to solve for z. I'm going to take the square root of both sides. And when I do that, I get z equal to, the square root of 36 is 6. And then I can break 27 into two factors, one being a perfect square, which is 9 times 3. Therefore, the square root of 9 is 3. That comes out. That gives me 3 times 6, which is 18. And what's left inside is just 3. Therefore, z is 18 square roots of 3. Now I can go find the value for y. Y is an altitude. And by corollary 1, the altitude is the geometric mean between the segments of the hypotenuse, which are 27 and 9. Then I use the cross product rule and get y squared. Again, I'm going to leave these two as factors, which is going to give me 9 times 27. Take the square root of both sides. That gives me y equal to, the square root of 9 is 3, times the square root of 27, which its factors can be 9 times 3, 1 being a perfect square. Therefore, y equals, the square root of 9 is 3. 3 times 3 is 9. And this 3 stays inside the radical. Therefore, y is equal to 9 square roots of 3. On this problem, we're at a golf course, and Maria drove her ball 192 yards straight toward the cup. So here, T represents the tee box. She drove it 192 yards, landed at M for Maria, and she drove straight toward the cup. Her brother, Gabriel, drove his ball straight 240 yards, but not toward the cup. From the tee off, he went 240 yards to G, which stands for Gabriel. And of course, he's not in the direction toward the cup. And that diagram represents those two striking distances. The diagram shows those results, and they want us to find x and y, the remaining distances from the cup. This is very similar to our last problem that we're led to believe to start with y. And if we do that, we can kind of do this in our head, that y is a leg. Therefore, corollary 2 tells me that I have a geometric mean that has y, and we have another unknown, which is the length of the entire hypotenuse. Therefore, that gives me an unknown of y, an unknown of the entire hypotenuse, and an unknown of the segment adjacent to that leg. So that won't work. The altitude of the hypotenuse really isn't needed in this problem, but I could use it if it would get me to a position of getting another known variable. But here, if I give this an unknown, I still would have another unknown with x, so that won't work. So the direction I need to go is by using that leg, which is 240 yards. So when I use that leg, I use corollary 2, and that leg is the geometric mean between the hypotenuse, which I don't know, but what I can do is either add these two together and let it be x plus 192, or an easier way to do it would be to just let this hypotenuse be one variable, which is h. So that leg's the geometric mean between the hypotenuse, which is h, and the segment of that hypotenuse adjacent to that leg, which is 192. Then I use the proportion by cross product and solve for h. Therefore, I get 192. H equals 57,600. When I divide both sides by 192, I get h equal to 300 yards. Now, h is 300 yards from that previous proportion. And now I can solve for x by just subtracting 192 from 300 yards. And when I do that, x is going to be 108 yards. Now I can use the same corollary 2, but using that with our other unknown variable, y. Therefore, each leg is the geometric mean. Y is the leg. It's the geometric mean of the hypotenuse, which is 300, and the segment of the hypotenuse adjacent to that leg, which is 108. Cross product, y squared, is equal to 32,400. And when I take the square root of both sides, I get y equal to 180 yards. Therefore, most of the time, it is a lot better to hit straight down the fairway and shorter, and that way you end up closer to the cup.